RL Circuits 2. Here we derive an equation for the rising time-varying current through an RL circuit, i.e. a circuit having a resistor R and an inductor L in series. When the switch is thrown to point 1, write the Kirchhoff's loop equation that applies. It doesn't matter, obviously, but we'll start at point 1 and proceed counterclockwise around the loop. When we throw this switch over to point 1, we're going to write Kirchhoff's loop equation. First thing we run into is the battery, which has a voltage of E. Then we run into the resistor that has a current I through it. And we could write this I with a T in parentheses after it because that is a current that is changing with time, but just to save space, we're going to write it little I. Quite often, whenever there is a current that is changing with time, it's represented by a lowercase I rather than a capital I, but that's sometimes just a personal preference. Anyway, we're going to leave it like that for now. Then we're going to go through an inductor right there, L, and we learned in an earlier video that the voltage for an inductor changes according to that equation right there. Then we're back, aren't we, to point 1. We've closed the circuit there. So there's our Kirchhoff's loop equation. And what is it about that makes it a differential equation, in case we've forgotten what a differential equation is? It's a differential equation because it has a variable, namely the current, and it has a derivative of that variable in it. That's what a differential equation is. It has a variable and a derivative. It doesn't have to be a first derivative. It is in this case, but it doesn't have to be. And now we're going to solve this baby. Here's how we're going to do it. We're going to lay this out for you. We're going to rearrange our part A answer so that the L and the dt terms are the only ones on the left with dt in the numerator. And I'm giving you a hint here. There should be one negative sign in our answer. We want the L and the dt terms on the left with dt in the numerator. If we do that, this is what we end up with. dt over L is equal to bi over E minus IR. And there's the negative sign right there. So hopefully that was okay. If we put the L di dt term on the right side of the equation, it becomes positive, and then we divide both sides by di, and then we take the reciprocal of both sides. Stop the video if you need to, but that's what you get right there. Now what we're going to do is we are going to show that we plan to integrate time from t equals 0 to t equals t, and we're going to integrate the current. The current is going to start from nothing, and it's going to increase to I. So we're basically going to rewrite the part C answer with these integration limits. So here we go. From t0 to t equals t, dt over L, and then we're going to integrate this side from I equals 0 to some later current I, di over E minus IR. So that's what we're doing. Now we're going to use U substitution to do this. We want to write what U is equal to, and namely the denominator of our part C answer, which is also right here. U is going to be E minus IR. Now we want to differentiate that with respect to I. If we differentiate this with respect to I, you differentiate the voltage here, that's nothing with respect to I, and on the right side, you simply get minus R. Let's rearrange this to say what di is equal to. Di, when we do this, di would be that, so minus du over R. Letter H here. Substitute the parts E and G answers. There's our part E answer. That way I didn't have to rewrite it. And there's our part G answer. And here's our part D answer. We want to substitute this thing and this thing into here and see what we get. The left side isn't going to change at all. We're going to integrate from t equals 0 to t equals t, dt over L, no change there. But the right side, we've got, you can see u in the denominator. So we need to integrate. I'll go ahead and just write the limits that we had originally. We're going to get u in the denominator. And then di is in the numerator. Well, di, you can see right here where I'm pointing, di is negative du over r. Negative du, and then we'll put r right there. Moving right along. Now we're going to integrate the left side of this equation that we wrote. Let's do that right now. That's real easy, isn't it? When we integrate that with respect to time and put in the limits, that ends up as just being t over L. So that was easy. Then we're going to move all the constants and the negative sign to the left side. What we had here in part H, r is a constant, and so if we move it to the other side, we're going to get the r in the numerator. Let's put the negative sign over there. And then what do we have left on the right? I equals 0 to I equals I. And all we have now is du over u. All right, letter J. Now, two more steps in one. Let's integrate the right side of part I and then unsubstitute the part E answer, which again I've rewritten here on the left side of the screen. We're going to keep the left side of this equation the same. We're going to integrate this side. When we integrate that, we're going to get the log of u. But we don't want to write u here. We want to say what u is equal to. So that's the log of e minus ir. And then our integration limits are from I equals 0 to I equals I. All right, we're nearly done here. We're going to substitute and evaluate the limits of integration on the right, and we're going to use a law of logarithms. So the left side stays the same, minus RT over L. We're going to put these limits in here. We are going to end up subtracting, but since it's logarithms, we can use division. If I put I in there, I end up with, in the numerator, E minus IR, and in the denominator, just E. And I'll put absolute value signs, but you can put parentheses if you want. Letter L, we're going to rewrite part K, but let's eliminate the large fraction line. Minus RT over L, natural log of, wouldn't this be 1 minus IR over E? Can you hang with me? We're almost done. Now we need to unlog this thing because the whole point is to try and find an equation for I. We need to get at I, we need to unlog this thing. So that means we need to e to the both sides, as I put it. So we're going to go e to the minus RT over L. And then when we e that side, we end up with 1 minus IR over the voltage. And lastly, then, we just need to solve this thing for I. If I put the IR over E thing on the left, it becomes positive. And then if I move this E to the minus RT over L on that side, that becomes negative, kind of like that, which means our equation for time, remember we said at the outset that we could have written little I as a function of time all along here, but we just didn't want to waste all that space and ink. Here you go. Let's put time 0 in here. If you put a 0 in here for time, that's e to the 0, which is 1. And that means at the first instant, the current will be 0, which is what we said happened with an inductor. At time equals infinity, if I put infinity in here for time, that's e to the minus infinity, which is 0. In essence, at time infinity, the current through the circuit is simply E over R, which is the inductor acting like an ordinary wire.